Okay, so today we're going to look again at connections and curvature, but from this slightly more geometric approach. So, David, when you did connections and curvature, how did you do it?
Just Christopher connection.
Sorry?
Just Christopher symbols.
Right, so not this more abstract way. Okay. So yesterday, when I was talking about bases, I was trying to sort of get across the fact that the connection was something which was a structure on the tangent bundle, and we could think of it intuitively as like stitching together neighboring tangent spaces in a particular way. It's a rule for how you transport your basis vectors from one tangent space to the next. So reflecting that, if we think about the connection components, that's going to show up in a rule that tells us how the connection acts on basis vectors. So this is how we define our connection, or our connection components. So connection here is grad, which is a derivation. Well, actually, we define it. I'll give you the axioms in a moment, but this is our practical way of looking at it. So the derivation acts on a basis vector, and it takes it to a mixed 1-1 tensor. So that's here the vector part, and these omegas are the dual basis to EA. So here, these gammas are a set of numbers, scalars, that give you this rule of how the vector basis changes as you move around on the manifold. So we could also write this as sort of taking the gradient of a basis vector and then contracting with a one form. So just as a reminder, dual basis means that when you have omega A as a form acting on EB, the vector, if A equals B, you get 1. If A does not equal B, you get 0. And of course, we've got no metric at this point. Okay? So in terms of a definition, what is the covariant derivative? So we have sort of three rules that it has to obey. It has to commute with... Yes, David?
Something wrong with your indices in the definition of the connection. So the first equation, you have three.
Oh, yeah, I've got three B's. It should be an omega A, shouldn't it? Yeah. So thanks. So the gammas, the first of the lower indices is always the one that's doing the derivative. So here, this A would be kind of associated with the grad. So you see that you've sort of added a one-form basis element here, and that index is tied to the first one. So I'm being strict about ordering here because at this point, I haven't made any assumptions about properties of the connection. And it turns out that to define grad, it's a derivation. So what that sort of means is it's something that's taking a derivative. So that ties in with this property of Leibnizian, which means if grad acts on a product, a tensor product, you take individually the derivative of each of the components of the tensor product and just add them together. If it's acting on a function, it just reduces to D, and it commutes with contractions, and this is a contraction, the one form acting on a vector. So you might say, well, this all seems very abstract, but I'm used to writing, okay? You're used to writing sort of grad nu, V nu, as a partial derivative. So you're used to that formula, that the gammas are what you add to the partial derivative to make it covariant. So what's going on here, okay? Because it looks like I'm acting on a vector, which is a basis element here, and yet I'm getting just gammas. So what's going on? So there's sort of two sides to this, or two parts of this. One is that I'm not making any assumptions about this vector basis, so I'm not saying it's a coordinate basis, not even saying it's an orthonormal basis at this point. But within the basis, it's sort of like saying that for a basis vector, the only part of this derivative expression is the second piece. So let's look at what happens if we act with grad on a vector. So this is the geometric thing. So this here is an element of T star of M, tensor T of M, as a vector field. It's got a covariant and a contravariant part. So if I ask what is this, well, the vector can be decomposed with respect to the basis, EA. So now I look at what this is. I use the Leibnizian property. So that's using the Leibnizian property. Now I use, so if you like, this is using the second of those requirements. I now use the third of the requirements to say that grad acting on a scalar is D, because the components of V are just scalars. I then use my expression up there for the gammas. And then I now decompose. DVA is a one form, so I can decompose it with respect to the basis, omega C. So that is VA, comma C. And then I'm going to just juggle around the indices here, swap the A's and B's. And what I find is the expression for grad V, the components of grad V, are indeed the corresponding partial derivatives, but expressed in the particular basis. So this is the expression that we would write down if we were using the abstract index notation. But you get it by just thinking about what the geometric object is and decomposing the derivative of the components of the vector and of the basis. So that's an example of the distinction between what we do with abstract index notation and what we're doing here with this sort of geometric notation. So that's all general. We don't need a metric to put a connection on the space. So in GR, we want a metric connection because, you know, our sort of physical observable is distance, and we want to think about what happens to distances as we move around on the manifold. So we kind of want our curvature to be associated with our metric function. So we choose the connection that annihilates the metric. So grad G is 0, and it's also a symmetric connection. So if we're in a coordinate basis, swapping those mu's and lambdas there gives us the same thing. But strictly speaking, what it is a torsion-free connection. So what is torsion? So we define the torsion of a connection. It's sort of more or less the antisymmetric part, not quite, but more or less. So we take two vectors, u and v, which are arbitrary. We take the sort of antisymmetric derivative of one with respect to the other, so grad u of v and grad v of u. And then we subtract off the Lie bracket because u and v themselves may not commute. And so that gives us an extra sort of antisymmetric piece. So when I say almost the antisymmetric part of the connection, this is where you see the difference between using coordinate bases and a general basis. So the coordinate basis, everything links. So remember we said the Lie derivative, or the Lie bracket, represented the amount by which a loop didn't close going along u, then v, or v, then u. If it didn't close, then the Lie bracket was non-zero. And correspondingly, u and v were then not sort of vector lines, or their curves were not curves of a coordinate basis. A coordinate basis is a unique labeling, so that means if you go around one side of a square, it's the same as going around the other side of the square, so that commutator vanishes. So if you're used to coordinate bases, then you would just say the torsion is the antisymmetric part of the connection. in a general basis, you can have these non-zero commutators, and so you have to kind of correct this anti-symmetric part of the connection also contains a bit of nonsense that's going on with the basis, so you have to subtract it off. So the torsion is a tensor, and you could sort of see or argue that by looking at coordinate transformations, the connection. But the reason you see it's a tensor is you look at its definition here. So here I've written this down without any reference to any basis. It's defined in a geometric fashion. And it's sort of independent of U and V. That's sort of indicating that this is a geometric object, therefore it's a tensor. So we set that torsion tensor to 0 for GR, for our Levi-Civita connection. So now I want to talk about calculating the connection components. So if you tried to well, I guess these days you probably wouldn't even try to do it by hand. You'd probably just quickly open a Maple Mathematica notebook. But I want to discuss a pen and paper way of calculating connections and curvature, which is very powerful. It's sort of very few calculational steps for computing curvature, because if you try doing by hand the Levi-Civita connection in, let's say once you get to 10 dimensions, for example, it becomes a bit of a nightmare trying to, recollect, have I summed over all these indices? Have I done this right? Have I made sure that I've gone through all the cases? It's a bit of a challenge, right? And even with the best of intentions, it's quite easy to make mistakes. So on the other hand, there's a method that I want to discuss, which is the Cartan formalism, which is more straightforward. If you have patterns in the structure of your geometry, it's very easy to kind of sort of roll those patterns in to the expressions you're dealing with and sort of save yourself a lot of grief. So I have to start with a definition. So I'm going to just take these connection components and just roll them into something slightly different. I'm going to make a one form out of them. And you'll also see this called the spin connection if you're doing supergravity. So what you do is you take the connection components and you mop up the differentiating index with a one form. So here, if you kind of look at what the grad is doing up at the top, that grad EB, it's equal to the spin connection contracted with the basis vectors. So the reason why this is useful and why I'm sort of pushing a little bit this formalism of taking basis vectors is that if you want to think about fermions on a curved manifold, you have to be able to figure out how to put spinors on the manifold, how to differentiate spinors on a curved space. So your gamma matrices, they have anti-commutation relations that usually take you to the Minkowski metric, the eta mu nu. So that's what your gamma matrices do. But eta mu nu is not curved. And so you don't particularly want to sort of start trying to think, well, what do I do to my gamma matrices in a curved space-time? Instead, you put one of these bases that's orthonormal. So you kind of hide your curvature in your choice of basis, and then you still use your straightforward gamma matrices. So you can still use your usual algebra in this orthonormal basis, but then your curvature's kind of now residing here, and when you take a derivative of your spinor, you kind of have this connection 1 form coming in. So this is the sort of rationale why this formalism gets used, and if you are doing supergravity, you'll need to use this method or this way of writing things. So what the Cartan relations do is they relate this spin connection and the torsion to derivatives of the dual basis. So it's a straightforward way of computing connection components. So I need to go through a couple of steps just to, yeah.
So the spin connection, does it transforms as a tensor? Because the connection does not, right?
Sorry, does it?
The connection,
Yes.
the usual connection does not transform as a tensor.
Right.
So does the spin connection transform?
So the bit that is geometric, is the 1 form piece. These are just scalars. Mm-hmm. So at the moment, so this is this difference of perspective between abstract index notation and this geometric notation. Here, I am simply taking a matrix of 1 forms. I'm making no statement about these indices. So I think I'm really glad you asked that question because it is highlighting this difference. So you should not think of these indices as tensor indices because they're not. They're just labels. So we do not hit the problem that gamma isn't a tensor because these are not tensor indices. Does that make sense? This is actually it's a sort of subtle distinction, and it can be a little bit, I don't want to say confusing, but it's just sort of, there's a slight mismatch between what you expect when you see these things and what they actually are. So the geometric object theta for a given A and B is geometric. It's a 1 form because of the basis vector. But the matrix theta AC is just a matrix of 1 forms. It is not components of a failed tensor. Right? Does that make sense? Sort of. It is, yeah, there is a sort of, I think it's like a hurdle, a little bit of it can trip you up this thing. Whenever you see indices in this part of what I'm writing, don't think vector, just think labels, scalars, set of scalars. Mm-hmm.
If you're calling it a scalar, then how are you contracting?
So here, this is just, these omegas are 1 forms, the basis. So what I'm doing is I am simply taking a combination of omegas according to these scalars here. And so I'm constructing this matrix of 1 forms here. So I'm not contracting, I'm just adding.
Well, but it still transforms under coordinate transformations, right? Because you could, they are labels, but it's the A component with respect to the basis E, A.
Yeah.
Okay.
So, but I've got my omegas here, so I have a basis and a dual basis. If I change my basis, and I were to do this whole rigmarole with a different basis, E primed and omega primed, my gammas would be different. And I'm not making any statement that they relate to these gammas at all. At the moment, I'm just saying I've chosen my basis, I've chosen my co-basis, or rather I've chosen my basis which gives me my co-basis, and associated to that vector field, I have painted, or rather I have a connection, so associated to that vector basis, I have a set of scalars, which are my connection components. I'm now going to use that sort of matrix, three-dimensional matrix of scalars to construct a two-dimensional matrix of one forms, and I'm not interested at the moment about transforming anything, because what I've got here, this omega is a one form, it's a specific one form, and that kind of tells me that it's something which is abstracted from the local chart. It's a covector field. I'm not saying it's easy, but okay, so the first step that we need is to make an observation about the metric connection. So for the metric connection, if I take the derivative of GAB, the components of the metric in the basis or co-basis omega, I get the symmetric part of these connection one forms. So to demonstrate this, d of GAB is equal to grad of GAB, because GAB are just scalars. They're a set of scalars. So what does it mean? The components of GAB, well, G is a symmetric rank 2 covariant tensor. That means it's a bilinear map from the tangent space times the tangent space into the reals. So I simply take two of elements of my basis vectors and contract with G to get the components. I now use the fact that this is a metric connection to say that grad G is 0, and I'm using Leibnizian property here. And I pull that the covariant derivative through this contraction. So it hits G, it gives me 0, and then I have to hit each of the basis vectors in turn. But each time I hit a basis vector, I get these connection components. So So that says that the metric connection has symmetric spin connection. And so this is now the importance of the orthonormal basis. If we have an orthonormal basis, then that means that if I can sort of take the metric or the distance function, you know, the dot product of EA and EB, I get 1 or minus 1 if A equals B and 0 otherwise. So in other words, the components of the metric are either plus or minus 1 or 0, so therefore its derivative vanishes, and I see that my connection is therefore antisymmetric.
Sorry, could you explain that again?
Yeah. Okay. So what does an orthonormal basis mean? It usually means, well, if you take the dot product of two different basis vectors, it gives you either 1 or 0, and it's only 1 if they're the same. Now, we have to make that a bit more general because we're in space-time, so we have a Lorentzian signature. So if EA and EB are, what it's saying is if EA and EB are different vectors, we get 0. If we take EA dot EA, we get either 1 if it's the time-like direction, minus 1 if it's space-like direction. So that means our components of GAB are basically the Minkowski metric. That's not to say that we don't have a curved space. What we've done is we've hidden all the curvature in the basis, choice of basis. So just like when we do spherical polars in R cubed, we have an orthonormal basis associated with spherical polars, but those basis vectors, you know, are d by dr, 1 over r d by d theta, 1 over r sine theta d by d phi. Now, obviously, that's not curved, but it has a non-trivial connection. And what we've done is we've packaged all the non-triviality of our coordinate system into the basis vectors rather than into the components of the metric with respect to that basis. So again, we're hitting this mismatch between our expectations for working with curvature and indices and this abstract index notation and this geometric way of looking at things where I've tried to always underline the geometric object, where our metric is a symmetric second-rank covariant tensor, but GAB are the components of the metric in whatever basis you happen to have chosen. So it does seem, it is quite abstract, but I've kind of got to get to the, to get to the punchline before I can then show you how it applies. And some of these things may then kind of slot into place a bit more easily at that point. So what we're going to do now is derive an equation which tells us what this spin connection is simply by differentiating the covector basis, omega A. So let's consider this antisymmetric product. Theta is a 1 form, omega is a 1 form, so I can take the wedge product of the two of them. And now I've just written out what the spin connection is there. So at the yep,
Excuse me, it's about the line about GAB equals eta again.
this one.
Yeah.
Yeah.
I'm just confused because, so I understand it's eta at like a point, but since we're taking a differential, doesn't it matter that like we want something local?
So it's saying that that is true at each and every point, and we've chosen our basis to make it so. So here's what I was saying before. dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. That's our metric, okay? That's our geometry, so to speak. It's flat space, but it's written in a sort of, non-flat form. So what would the basis vectors be here? So it's actually easier from this way to do it to start with the covector basis. So I would define my omega r as dr. My omega theta is r d theta. And my omega phi is r sine theta d phi. So that's how I would define my basis of one forms. And you can sort of see that my ER would be d by dr. E theta would be d by d theta, but with a 1 over r. E phi would be 1 over r sine theta, d by d phi. So if I ask what is the length of each of these vectors, so in the basis, if you like, this is just 1, 0, 0 in coordinate basis. Yeah. This one is 0, 1 over r 0, again in the coordinate basis. This one is 0, 0, 1 over r sine theta, again in the coordinate basis. So now now that I'm in the coordinate basis, I can decide what the length of each of these is because I know my rule for distances. This is the sort of shorthand for the metric. So here, if I ask what's the norm of ER, well, I just get 1 because it's just 1 there and that's a 1 there. The norm of E theta, well, I've got 1 over r twice for each E theta, and I've got an r squared there, so that's also 1. And similarly, the norm of E phi is 1. So if I now ask what is the rule, if you like, the GAB, so I'm now asking if I were to sort of say, if I now decompose vectors, instead of decomposing them in the coordinate basis, I'm going to write a vector as a combination of ER, E theta, and E phi, then I would simply take if I wanted to know its length, so say I've got a V, which is sort of VR, ER, and plus a V theta, E theta. So I now decompose it here. I've sort of put the 1 over r hiding there. So the norm of V here would be the square root of VR squared plus V theta squared. So that's like your, put hats on it. So this V, the component of your vector in the orthonormal basis, is different from the component in the coordinate basis by a factor of r. So you're kind of hiding the non-triviality, or in this case it isn't curvature, but the non-Cartesianness of your metric in the expression for the basis elements. So this is why sometimes people sort of think of this as the square root of the metric, because you're kind of saying, well, you've sort of taken these functions and square rooted them in here. So it's I mean, and it's eta AB everywhere on the plane, or delta AB everywhere on the plane, because those expressions that I've written down are not just valid at a single point, they're generally valid.
So
If that helps.
for any metric, or
Sorry?
can you do that?
Not any metric. That's quite an interesting question. So most of the metrics that we meet, yes, you can do this. And in fact, it's related to the spin structure. If you can, when you can do this in a way that's essentially global, then you can put spinors on your manifold, okay? But some metrics do not admit this sort of global or pseudo-global orthonormal basis, and then you can't put a spin structure on it. So obviously we want metrics that can have this decomposition, because we want to put Fermi on. We have Fermi on. We've got no choice, right? So, so you will always see anything that we will discuss. I'll always be able to hide it in an orthonormal basis. Okay, so here I was just playing around, pushing symbols around. Not really doing anything deep. I've just translated the one form into the connection components. Because this is a two form, it's antisymmetric, which means it only picks up the antisymmetric part of gamma. And then the antisymmetric part of gamma is, of course, related to the torsion. It's not quite the torsion. We've got these structure constants floating around, but I can just use this relation to replace that antisymmetric part of gamma. But now, I use the fact that these structure constants are the Lie bracket of the two basis vectors. And so what I've done here, this is the torsion tensor. I've related this wedge product of the spin connection with the basis one forms to the torsion and this other piece here. So this at the moment is something that's not particularly helpful, but we had a relation between the Lie bracket and D. So if you remember that if you have a covector acting on the Lie bracket of two vectors, it's the same as the exterior derivative of the one form acting on the individual vectors. So I'm looking for the identity, which I haven't brought with me. Okay. Okay, let me get this up. So we had this identity relating D and the Lie bracket, so I've written it out there. But the first two terms of that identity vanish because omega is a dual basis to E. And so what this is really saying is that that term that I said wasn't very helpful, that I've circled, I can rewrite as D of omega. Okay. So, yep.
But why do the terms with the deltas disappear?
Because delta is either 1 or 0. So if you're, remember that the one forms are a map, sort of taking you from vectors down into the reals. So all that is, if you look, sorry. So that means EB, so EB is a tangent vector. The tangent vector takes the derivative of a function at a point. But if you look at what it's acting on, the scalar it's acting on is the combination omega A of EB, which is just a constant delta AB. So because you've chosen, in general, that identity would be D of some omega acting on UV, and then in that case, you'd have omega of V or omega of U, which would be some actual non-trivial function. Here, because we're using basis vectors and forms, everything is just 1 or 0. And when you take the derivative of it, it's 0. So for the basis vectors, I can use that to replace this Lie bracket term here. I can sort of shift the derivation part of it from here to here. But this is just, if I look at this, these are just the components of d omega in the basis in EB, EC. So these are the BC components of omega. But then first of all, I do that to get the scalar components of d omega. But then I re-promote it back to a 2 form by taking this omega B cross omega C. So this whole second piece is just D of omega A. And so if the torsion vanishes, I can find my connection components which by simply differentiating the basis 1 forms. So I've now got a set of rules to find that matrix of 1 forms, theta AC. I know it's symmetric if I lower the A index, and I just take the derivative of the basis to get the non-trivial components. So this is Cartan's first structural equation. And I've got a simple example at the end, and I'll show you how to apply it. But just to sort of complete the story, I want to write down Cartan's second structural equation, which I'll do without proof. So first we need the curvature of the connection. So curvature, just like when you do gauge theory, sorry, you don't call it curve, I suppose. Well, anyway, so your Maxwell stress tensor or the equivalent field strength, if you have a non-abelian gauge field, is defined as a commutator of gauged covariant derivatives. And so if you just have an abelian gauge field A, then that simply gives you d mu a nu minus d nu a mu, the commutator of gauge covariant derivatives. If you've got a non-abelian gauge field, you get the sort of space-time derivatives plus a commutator of the two gauge potentials. And it's pretty much the same here. You're taking grad u grad v minus grad v grad u. If that were u and v were coordinate bases, that would be the end of it. But if u and v are general vector fields, then you also have to take the commutator of u and v. So you can kind of see this as directly sort of analogous to what you do in gauge theory. So it's the same sort of idea. It's the curvature of the connection. And R, if you see what it's doing, it's taking three vectors and it's giving you a vector in the end. So it's a map from three copies of the tangent space into the tangent space. So that's kind of what it does. Physically, it tells us about tidal forces. Which are, of course, the sign of true space-time curvature. So when Einstein was developing his theory of general relativity, he sort of started off by thinking about the equivalence of accelerating frames and us on the surface of the Earth, and realized that, with freely falling frames, if you're in a freely falling frame in a gravitational field, you couldn't necessarily distinguish that from an inertial frame to leading order. The only way you would know you were in a gravitational field would be by watching things slowly sort of creep together or move apart. So in components, just write down. So in components, the components of the Riemann tensor are sort of what you would expect, what you've already seen in the coordinate basis, sort of the anti-symmetrized partial derivative of these connection components, the anti-symmetrized gamma-gamma pieces. And the only thing that it's probably not familiar is the last term, but that last term has to be there if you have a general basis with these non-zero commutators. So I'll just tell you about Cartan's second structural equation. So I'm sort of claiming that you can find connection components by taking derivatives of the basis one forms. And so what I want to do is to get a definition of curvature in terms of derivatives of the spin connection. So because the spin connection is a one form, That means I have to define a curvature 2 form. And what I do is I mop up the last 2 indices of the Riemann tensor. So what I'm essentially doing up here is taking the sort of UV part and kind of pulling out the UV and making this instead into a 2 form. So once again, confusing bit. The geometric part of this expression is the 2 form part, omega c cross omega d. The A and B are labels, and it's a matrix. It's a matrix of 2 forms. We're not doing any coordinate transformations at all on those indices. So Cartan's second equation relates the curvature to a derivative of the spin connection plus commutator, or what cross product of spin connections. So again, that will kind of be familiar from a gauge theory expression. So just to sort of do some very simple example of this, kind of related to that. So let's just see r squared in polar coordinates. So I've already said that I'm going to make omega r equals dr. So that tells me d of omega r is 0, because d squared is 0. Omega theta is going to be r d theta, and d of omega theta is therefore dr cross d theta, which is 1 over r er cross e theta. So from Cartan's first structural equation, I can read off, I mean, there's only going to be one non-trivial component here because it's a 2-dimensional space, but I see that I have theta from this one, theta theta r is 1 over r omega theta. So I get a non-trivial connection, but I've only really got one component, which is the one independent component, the theta r piece, and there's no RAB. Because if I take d of this, I actually get 0. So if I look at now the 2-sphere, my omega theta is d theta. My d of omega theta is 0. Omega phi is sine theta d phi. D of omega phi is cot theta omega theta cross omega phi. So I can read off my connection, one form, and this time this, which is equal to cos theta d phi, does not have a vanishing derivative. So r phi theta, which is d of theta phi theta, is minus sine theta d theta cross d phi, which is equal to omega phi cross omega theta. So that means I can read off, and I'm just going to put hats over here to emphasize this is in the orthonormal basis, though actually for this example, it doesn't matter. So our phi theta is equal to 1. And then you get the other components by sort of the symmetries of the Riemann tensor. So that's sort of deriving all of the non-zero components of the connection and the curvature for the two-sphere. Now, probably in 2 dimensions, it's a close call of which is the more efficient because there's only 2 choices for each index. So lots of things vanish if you were doing it using the actual component method. Nonetheless, it's pretty quick. You know, I've just sort of done that in a couple of lines. So what we'll do tomorrow is we'll look at this example for essentially black holes. So we'll look at a spherically symmetric space-time, and I hope to convince you that this method is kind of a lot more reliable and faster than kind of going through component by component. So, and it also gives David time. He's fiddling with the notation or something, I think, on the handout.